Dear student, today we are from Gujarat University Department of Statistics, and I am Pravendra, and with me my senior colleague Dr. C.D. Bhavsar. In last lecture we have discussed analysis of variance for one-way classification and two-way classification, and today we discussed CRD, RBD and LSD. These are the complete block designs in design of experiments, and today we discussed with brief in CRD, RBD and LSD.
Dr. Parvinder had completed his PhD in design of experiment. He is an expert in design, and we see how he taught you about the design of experiment in details. So, Parvinder is there.
Completely randomized design. In short form, we call it as CRD. This is the simplest design, which is based on the principle of randomization and replication. In design of experiments, we study there are three basic principles: randomization, replication and local control. In CRD is based on randomization and replication only. Now suppose we have V treatments. We have V treatments and and homogeneous plots of say equal size and shape. Now we do not note down this point. We do not know any type of variation in the plots. We do not know any type of variation in the plots, any type source of variation. In the plots. And now we divide say V treatments into n plots such that randomly. This side we take treatments. So there are V treatments. We divide or we apply these treatments randomly to these plots, say, and the observation, say it is y11, y12, say y1, r1. Here it is r1 plots. Yield or response for second treatment in this plot is 2-1, say y22, and this is y1, say r2. This is yv1, yv2, vth treatment, and this is y1, rv, r2 plots. We apply treatment 2 in r2 plots, we apply treatment 1 in r1 plots, and we apply treatment v in rv plots. And the sum of this j takes value 1 to v rj is n. Total are the n plots. Total are n plots. We divide n plots in such a way and allocate the treatments from 1 to v. So this is how we divide or how we allocate different treatments in n plots. Here R1 and R2 and RB may be different, but the sum should be equal to n. Now we consider the mathematical model for this completely randomized design. Now, let mana yjk is the yield or response, or you can say response from the kth plot receiving jth treatment, and this is equal to yjk will be is equal to mu tau j plus ejk, where tau j it is mu j minus mu, where mu is the general mean effect and tau is the effect due to jth treatment, and this is eijk is the error effect, and eijk follow normal distribution with mean 0 and variance sigma square e. eijk are identically and independently distributed normal variates follow normal distribution with mean 0 and variance sigma square e. Now we try to find the values of mu delta j, and subject to the condition that the sum j takes value from 1 to b, rj delta j should be 0. Call this as equation 1 and call this as equation 2. Now using the principle of least squares, we try to minimize the sum of squares due to errors. E is equal to, say, where j takes value 1 to v and k takes value 1 to rj, e j k equal to summation, double summation, j takes value from 1 to v and k takes value from 1 to rj. From this equation, this is yjk minus mu minus tau j square, and now we differentiate it to find the value of mu. First we differentiate it partially with respect to mu. So when we differentiate, we will get dE minus 2 j takes value 1 to v and k takes value 1 to rj, yjk minus mu tau j, and put it equal to 0 and put it equal to 0, and this implies simplify. So this will be j takes value from 1 to v and k takes value from 1 to rj, yjk, and this will be, when we add it is simplify, mu is constant, so we takes it just outside mu, and this is k equal to rj minus j takes value 1 to v, k takes value 1 to rj tau j, and this is equal to 0. Now further simplify this. We get this is equal to j takes value 1 to v and k takes value 1 to rj, yjk, simplify this, k takes value rj, so mu, j takes value 1 to v, say rj, and this is value is summation j takes value v, and this is rj tau j equal to 0. So we will get from this equation this implies j takes value from 1 to v and k takes value from rj yjk minus this is the value of n, so this is n mu, and this value subject to the condition this is 0, so this is now, so this is 0, so from here we write it as the value of estimated, it is j takes value from 1 to b and k takes value from 1 to rj yjk divided by n. So this is the value of estimated mu, and for notation we call it as y dot dot. We can also write it as y dot dot. So keeping this in mind and this subject to the condition, the value of mu cap is j takes value 1 to b, k takes value rj, yjk divided by n, and we also call it as y bar dot dot. Now this is the value of mu. Now we try to find the value of tau j by differentiating it with respect to tau j. Now differentiate it with, we get this is delta E delta tau j. Differentiate with respect to, we get minus 2 summation from k to rj yjk minus mu and tau j, and put it equal to 0. Now simplify this, we will get k is equal to 1 to rj yj minus, because mu is constant, so it is k equal to 1 to rj minus one to rj tau j, it is equal to 0. So this will be from here k equal to 1 to rj yjk, and this is rj because this is constant, so nu, and this will be rj tau j equal to 0. So by simplification, the value of tau j, this is summation k takes value 1 to rj yjk minus, from here it is rj mu. So the value of tau j estimate will be k takes value rj yjk divided by rj minus mu. Because we have already estimated it, so we write here this. So sometimes we also write like this, it is y bar j dot minus y bar dot dot. So, or in some books you may find this is the value of mu j and this is mu. So by this way we find the value of mu and the tau j. Now for the calculation purpose we write Now after finding the value of mu and tau j, we find total sum of square TSS, or we write it as total TSS. Total sum of square is the sum of square due to all observational contrasts. And this we write in this way: j takes value 1 to v and k takes value from 1 to rj. This is yjk minus y bar dot dot square. This is equal to, and in place of y bar not we see in some books we write for simplicity it as mu. So this is equal to j takes value 1 to v and k takes value 1 to rj, y square jk minus g square over n, where g is summation j takes value 1 to b and k takes value from 1 to rj yjke, that is sum of yield from all the plots, that is the value of g. And the degree of freedom here it is n minus 1, because total observations are here n, so degree is n minus 1. Next we find treatment sum of squares. Sum of square due to treatments. Treatment sum of square, or we write it as SST, is the sum of squares due to the best linear unbiased ST blues of all treatment contrasts, and this is given by j takes value from 1 to v, tj, tau j, where this is say L, so sum of where j takes value v, Lj, it is always 0, and is SST, sum of square due to treatments, is given by j takes value from 1 to v, rj, y bar j dot minus y bar dot dot whole square, and this is given by say j is equal to 1 to v t square j naught over rj minus g square over n. This depends on us whether we are using this form or we are using this form. Now after finding the value of total sum of squares and SST, where now here Tj, where Tj naught, it is given by summation k takes value 1 to rj yjk, that is jth treatment total. Now more generally, we write we partition the total sum of squares as j takes value 1 to b, k takes value rj, yjk minus y bar dot dot whole square like this. This is j takes value from 1 to b, rj, y bar, j dot minus y bar dot dot whole square plus j takes value 1 to v and k takes value from 1 to rj. This is yjk minus y bar j naught whole square. This is total sum of squares. This is sum of square due to treatments plus this is sum of squares due to error, SSE. Here degrees of freedom are n minus 1 and here it is v minus 1 and here it is n minus v. After finding the value of total sum of squares and SST, sum of square due to treatments and sum of square due to error, we put these values in ANOVA table. Here we write first column is source of variation, and here we write degrees of freedom. Here it is sum of squares and here it is mean sum of squares, and here F test. First we write sum of square due to treatments, and second sum of square due to error. And here it is total. By writing the total degrees of freedom are n minus 1 and this is v minus 1 and here it is n minus v. Here we write the value of total sum of squares due to treatments, sum of squares due to error, and here we write mean sum of square mean square error due to treatments, and here it is MSE, and we write the value of n by comparing MST by dividing MSE. And here degrees of freedom for F will be V minus 1 and N minus V. And we test the hypothesis for the homogeneity of means, and by comparing the value of F with the tabulated value at a given level of significance, we accept or we reject the null hypothesis as the value given by here by f. So this is the analysis of variance for completely randomized design. Now, completely randomized design is simplest because here the third principle of design of experiment we not apply. It is based on only first two, that is randomization and replication. So CRD is very simple, and if any value or any observation missing here, then then calculations may not be difficult for us. Now, in pharmaceutical companies, generally we apply CRD designs. We rarely used CRD in field experiments where the plots may not be homogeneous. Their plots generally we find in heterogeneous form. So CRD may be used in chemical factories for the testing of hypothesis by applying different drugs, because here the number of replications for different treatments may be different. So this is one of the advantages of the CRD. Randomized block designs generally based on two-way classification, and I just give you an idea of RBD here. And the analysis of variance for RBD is based on two-way classification. Now here suppose these are the blocks. Say here we take block and this side we take treatments. So here we note down treatments 1 to V, and there are blocks 1 to there. So it is V cross B matrix, and the yield by applying treatment 1 to block 1 will be Y1 by Y12, similarly Y1B. This will be Y21, Y22, Y2P. YV1, YV2 and YVB. And by constructing mathematical model that Yjk is the response from kth plot receiving the jth treatment, is written as mu plus tau j, similarly beta k e j k. This is the mathematical, and by applying the analysis of variance for two-way classification, we can find, or we find the ANOVA table here by finding total sum of a square as we calculated for CRD, sum of squares due to treatments, sum of square due to treatments, say row, sum of square due to rows, sum of square due to columns, or you can sum of square due to from blocks, that is column wise, and SSE, sum of square due to errors. And then we find the value of F by comparing mean or sum of squares due to treatments with SSE and SSB with SSE for blocks, and we find our result whether we reject our hypothesis, null hypothesis, or reject the null hypothesis. Similarly, we go for latent square designs. Where we find V cross V only number. For example, there are 16, so we take 4 cross 4 blocks, and by applying the principle of randomization, replication, and local control, we find the results of latent square designs also. Now I take an example of first CRD. Where we can apply CRD. For example, the following table example of CRD. Following table shows the yields in quintals per acre of a certain variety of wheat grown in a particular type of soil treated with three chemicals say A, B and C. A, B and C. We get the following observations. A, B, C, 48, 49, 50, 49, 47, 49, 48, say 48, 49, 51, 50 and 50. Now, following table shows the yields. These are the yields in quintals per acre of a certain variety of wheat grown in a particular type of soil treated with three chemicals A, B and C. Chemicals may be fertilizers. There are three fertilizers, for example, and we apply fertilizer A in these four plots. The four plots here. We apply fertilizer B, say, in another four plots. And we apply third fertilizer in another four plots. So total number of plots are here 12. Total number of plots. As theoretically, here R1 is 4, here R2 is 4, here R3 is 4. So total number of plots are here 12, and for the variety of, to know the effect of fertilizers on a particular variety of wheat, we get following observations. And now finding the value of total sum of squares. Total sum of squares due to treatments, that is fertilizers, sum of square due to error, and then we find the value of F by MST over MSE. And if we take null hypothesis that the effect of these three fertilizer is same, and after getting the calculated value of F at given level of significance, suppose we want to test it at 5% level of significance or 1% level of significance, we compare this tabulated value and calculated value with the tabulated value, and on the basis of if calculated value is less than tabulated value, we accept the hypothesis, otherwise we reject the hypothesis as in our literature. So this is the example where here the number of plots are same. for fertilizer A, for fertilizer B, and for fertilizer C. We apply fertilizers for same number of plots for a particular type variety of wheat. Now we take another example where the number of plots may be different for our treatments. Let we take another example. Another example, following table shows the lifetimes in hours of following table shows the lifetimes in hours of samples from three different types of television tubes manufactured by a company. For example, we note down sample 1, sample 2, sample 3. There are 3 samples, and here it is 407, 411 hours and 409 hours. And for second sample, we take values 404 hours, 406, 408, 405, 402, say. And for third, it is 410, 408, 406 and 408. Or if we like this, we write in this form. Now, if we compare this example with previous example, there are 3 fertilizers, and here are also 3 samples, sample 1, sample 2, sample 3. But here R1 is 3, R1 is 3, and here R2 is 5, 1, 2, 3, 4, 5, and R3 is here 4. So this is the case when number of say plots is different for different type of treatments. For here for sample 1, R1 is 3, and for sample 2 is R2 is 5, R3 is 4, and the total plot you can say here it is 4 or 5, 9, and 3, 12. So here in CRD it is written that R1, R2 and R3 may be different. So this is the one of the advantage of completely randomized design. Now if we consider an example of RBD, take another example of RBD. Like previous example, if we apply three chemicals ABC, and three types of say crop, 1, crop 2, example of RBD, randomized block design, say crop 3rd and crop 4. This is 4 cross 4, sorry 3 cross 4. V is 4 and there are 4 blocks, and if we note down the values, say example it is 3.5, 5.4, 7.6.3, 6.8 say, and it is, for example, that it is 5.8, 5.8, 5.7 and say 5.3. Similarly, if you take it is 6.8, 6.3, 6.4 and say 4.4. And by applying two-way analysis of variance for RBD, we can find the value of total sum of squares. Here number of rows are 3. Number of rows 3, number of columns 4, number of columns 4. So like CRD we find sum of squares due to treatments or row, sum of square due to blocks say or column, and sum of square due to error. And by putting the values in your ANOVA table, we test the hypothesis whether the effect from 3 fertilizers is same or not. So this is the example of RBD. Similar type of examples we can take Latin square designs. So but due to the time limitation I cannot take that. So this is the way how we apply CRD and RBD in different type of fields. So if is there any question, then we try to answer. No? Thank you.